describing circular motion in space. By the end of this lesson, we should be able to describe the motion of an object traveling in a circular orbit and an elliptical orbit. There's a lot of vocabulary here. Celestial mechanics is the branch of astronomy and physics that deals with the motion of celestial objects under the influence of gravity. The gravitational constant, capital G, is another constant. This time it's a constant of proportionality in the universal law of gravitation equation. It's approximately 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared. The inverse square law is a law stating that a specified physical quantity or strength is inversely proportional to the square of the distance from the source of that physical quantity. Kepler's laws of planetary motion are a set of laws that describe the motion of planets and their celestial bodies in their orbits, which were fundamental for the development of the universal law of gravitation. A massive body is an object with a significant amount of mass, like a planet or a star or a moon or an asteroid or whatever. Newton's law of universal gravitation says that every point mass attracts every other point mass by a force acting along the intersecting points of a line that connects the two. An orbit is the path that an object, like a planet or satellite, follows as it revolves around another object under the influence of gravity. An orbital period is the time that it takes, or the time that it would take, for an object to complete one orbit around another object. A point mass is a theoretical concept representing an object with mass concentrated at a single point, often used for gravitational calculations. Separation distance is the separation between two centers of masses, which affects the strength of the gravitational force. In an effort to advance humans' understanding of how the universe works, we'll look to the Danish nobleman and astronomer Tycho Brahe, pictured on the left. He meticulously recorded planetary observations so well he was given his own island and castle and 1 to 2% of the king's salary by King Frederick II, so Brahe could be left alone to gather data about the planets and stars. This was perhaps the largest investment in science ever. But his data is so good that it is still usable today, nearly 500 years later. He could not do all this work alone, so he hired the genius mathematician Johannes Kepler. But Kepler assisted Brahe and was never allowed to peek at the data that Brahe had been collecting so meticulously. The data was instead used for Brahe's own model of the universe, pictured here, which was also wrong. As you can tell from the mustache, Brahe was clearly a party animal, and the legend says that one evening Brahe was hosting a party and was engaged in a lively discussion with other guests. As a result, he ignored signs from his body to use the restroom, and his bladder burst. The resulting infection led to his death in 1601. However, another legend claims that Kepler was so eager to access his data that he poisoned Brahe. After Brahe's death, his family and Kepler fought over access to the data, and eventually Kepler was granted permission to use it and access it. From there, he formulated his 3 laws of planetary motion, forever altering our understanding of the universe. Picture Johannes Kepler. Kepler's first law states that planets move in elliptical orbits with the sun at one of the foci, not in perfect circles as previously believed. You may recall that in order to make an ellipse, you have to have 2 foci. The other foci is a mathematical point with no object occupying that space. For objects in elliptical orbits, the net force is always directed towards the focus that is exerting the gravitational force. This means that at almost every point except the 2 where the gravitational force are normal to the path, here and here, there is a component of the gravitational force that's tangent to the path. If you have a force that's tangent to the path, that means there's a tangent acceleration, which means as we're going through orbits, we're speeding up and slowing down at certain points. Earth moves in a faster orbit when it's closer to the sun than when it's far away. His second law, known as the law of equal areas, tells us that a line segment joining a planet and the sun sweeps out equal areas in equal time. When near perihelion, which is closest to the sun, that area is wide. Meanwhile, while near aphelion, farthest from the sun, the sweeps are long and narrow. Regardless of the shape, the area is the same for equal lengths of time. This will be useful when we consider the energies involved with the planets later on. For the third law, the law of harmonics, this connects the time that it takes for a planet to orbit the sun with a distance from the sun. Specifically, the period squared is proportional to the semi-major axis cubed. Semi-major axis is the bigger radius, the longer one, from the aphelion to the focus. This will be the law that we're most concerned with in this class and should be the law you remember best. So 78 years go by and there's still no mathematical proof for Kepler's third law, even though all of the data shows it experimentally. We still don't have it theoretically. In 1687, in the book The Mathematical Principles of Natural Philosophy, English translation, Isaac Newton formally published his 3 laws of motion, an explanation for the invented math, calculus, and the universal law of gravity. The latter says there's an attractive force between two masses that is proportional to the product of the masses and inversely proportional to the distance between their centers squared. Later, Newton added a constant of proportionality, which we call the gravitational constant, capital G. F sub g is a gravitational force, big G is a gravitational constant, m1 is one mass, m2 is the second mass, and r is the separation distance between the centers of those two masses. Universal implies that this equation works everywhere. However, we now know that this equation does not work around really massive objects like black holes. For those situations, we would need to use Einstein's theory of general relativity, not in this class though. Instead, whenever we are figuring out the gravitational attraction between two objects, we use the separation distance r between the center of masses squared. Remember that gravity always acts from the center of mass. The inverse square law says a specified physical quantity is inversely proportional to the square of the distance from the source of that physical quantity. In that case, the distance between the centers will be our separation distance. So if we have a planet and a sun, we're looking at the separation distance between the center of mass of the planet and the center of mass of the sun, because gravity always acts from the center of mass. In this instance, if you double the distance, you're cutting the magnitude of the gravitational attraction into 1/4 because of this inverse square law. Fundamental, we mean the simplest we can break a situation down into. In the universe, there are 4 fundamental forces. The strong nuclear is the force responsible for holding the nucleus of atoms together. If you'd wondered how 2 protons can exist in the same vicinity when like charges repel, it's because the strong nuclear Velcro-like force. This is the force related to E equals delta mc squared. The electromagnetic is the force responsible for protons or electrons repelling each other. In fact, when we say there's a normal force, we are actually giving a name to the electromagnetic force. You can think of the normal force as a result of the electric force between atoms. When 2 atoms are close together, their electron clouds repel each other. This repulsion is stronger than the attraction between opposite charges in different atoms. Therefore, when you press 2 objects together, their atoms resist being squeezed into each other by pushing back with an electric force. The electric force is what we call the normal force. The weak nuclear force is the force responsible for neutron decay and radioactive emissions, active at a short range. Finally, we have the gravitational force, which we aren't really sure how it works on the subatomic level using quantum field theory. Albert Einstein gave us a better understanding that works more universally than Newton's law of universal gravitation. In this, Einstein shows that gravity is not a force, but a curving of space-time caused by mass or energy. However, this is still incomplete at the fundamental level, so as of this recording in 2023, there is no understanding of how gravity really works. An expression for the period of a planet M orbiting a star mass big M that are separated a distance capital R. This looks like a force situation. So we're going to use our 4 steps. Start with a free body diagram. Let's assume this is a circular orbit, so we'll put our planet, our green planet, at a point where we can have just a centripetal force around this, directed leftwards. And that force is going to be our force of gravity. Says the stuff that makes it go, and if we're going around a circle, the stuff pointed inwards towards the center of the circle minus the stuff pointing out of the center of the circle equals mass times our centripetal acceleration. At Fg equals big G times m times big M over r squared equals mass times v squared over r. Let's think what v is here. Remember, v equals a distance over a time. If we're traveling all the way around the circle, the distance that we're traveling is 2 pi r. So we have 2 pi r over the time that it takes for one complete orbit, which is our period, and our velocity is squared, divided by r. What that becomes is 2 pi r 4 pi squared times r squared over t squared over r times m equals g times little m times big M over r squared. The little m's will cancel out on each side. We have r squared on the left side, so I'll multiply r squared to r squared. And then I'll erase and bring the problem up here. If you're following along, hopefully you've got extra sheets of paper. Right. So that's the old piece here. On the left, g times big M equals 4 pi squared times r to the 4th divided by t squared times r. R to the 4th and r, so that r goes away, and that r becomes cubed. I'm going to multiply t squared on each side. Remember, that's what the problem's asking us for. And we have t squared times gm equals 4 pi squared times r cubed. Well, look at what we've done. We have r cubed and we have t squared. Those two are directly proportional to each other. T squared proportional to r cubed. We have just proved Kepler's third law of planetary motion. And that's how Isaac Newton did it, using his law of universal gravitation. He started out thinking that if there was a cannon on Earth and that cannon was launched, the cannon would travel some distance. If it was launched faster, it would go even further. If it had enough speed, it would fall towards the Earth and continue to miss it, and it would be in orbit. For our exaggerating the orbit to be a circular orbit, just making an assumption that the orbit is close enough to a perfect circle, which is typical and allowed. If it's an elliptical orbit, then we have to know that we're speeding up as we get closer to the body that we're orbiting, and we're slowing down as we get further away. Example, planet X has twice Earth's mass and 3 times Earth's radius. The magnitude of the gravitational field near the surface is mostly what? Okay, so our gravitational field, well, let's just think about acceleration. Acceleration is our net force divided by mass. If the only force acting is our gravitational force, mass of the object and mass of the planet divided by r squared over mass of the object that's moving equals acceleration. Mass of the object cancels, and what we're left over with, g times mass of the planet divided by r squared. This gives us our gravitational field. This is the gravitational field equation. For Earth, we would use g equals 6.67 times 10 to the negative 11. For the mass of the planet, we would use the mass of Earth, about 6 times 10 to the 24th kilograms. And for r squared, we would do the radius of the Earth, because gravity acts from the center. And if we're on the surface of the Earth, then the radius of the Earth is going to be that, which is 6 times 10 to the 6th-ish meters. So we'll look at our gravitational field strength equation and relate what's happening on this other planet. We know the gravitational field strength on Earth is 10, or about that. Let's see what happens. So we have twice the Earth mass. So this equation becomes big G times m over r squared. I like to put what I'm doing to the mass just kind of off to the side, because whatever I do to the right side of this equation, I have to do to the left side of the equation. That's going to tell me how to handle this. So if I'm doubling the mass and I'm tripling the radius, then what I'm going to end up with is 2 over 9. 2 over 9 times g, or 2 over 9 times 10. Whatever that comes out to.